Welcome back to the series of lectures of high performance scientific computing. As we come to the conclusion of this course, we will now look at the future direction of microprocessors. So first of all, we need to ask the question, why do we need newer computing architectures? And we have discussed this in detail that there's going to be an end of the Moore's law. Moore's law had stated the fact that the amount of microtransistors that you would be able to pack within a square area is going to double every 18 months. But as we go down to lower and lower feature sizes, we're going to see the demise of Moore's law within the decade. Similarly, Dennard scaling, which was dropping the voltage and other associated electrical properties, has already sort of reached its limit. So definitely now the only way we can increase our compute power is by looking at newer architectures. So there's a growing demand of computing power both in artificial intelligence, edge computing, and also there's a big demand in the energy efficiency of these computes. There are quite a few key emerging trends which we have discussed. We have looked at heterogeneous architectures where we use CPUs, GPUs, and accelerators. Through the course, we have discussed on how to program in such environments. Going forward, there are domain-specific architectures, and also there is cloud-based high-performance computing. And we will now see in today's lecture what are the future promises and the future challenges of these kind of environments. So what are the challenges that are driving the microprocessor innovation? One is obviously the power and energy efficiency constraints. The second most important thing that we think about is memory and storage bottlenecks. As the era of computing grows, there is a lot more data that becomes available, and there's a lot more data that needs to be processed. And all of this needs to be stored in some sort of permanent storage, and plus during the compute, it needs to be stored in the memory. Obviously, there is increasing complexity in both artificial intelligence and high performance computing workloads as we do more and more sophisticated calculations. And obviously, there are security vulnerabilities in new modern microprocessors, which we have to deal with. So let us see how the CPU architectures have actually evolved over the decades. First of all, there has been an evolution from single core to many core architectures. Somewhere at the end of the turn of the last century, we were using only single core machines, and then we slowly transitioned into using dual core machines. Today, it is very normal to find even small handheld devices like cell phones which have multiple cores. Our desktops and servers have usually somewhere between 8 to, on the server end, even up to 256 cores. So we definitely are in the era of many core computing. There have also been significant improvements in the instruction set architectures, in the sense that each of the computing cores is able to take ever larger instructions and has more complicated functionality. We also have advanced capabilities like speculative execution and out-of-order processing. So now there's a strong rise in heterogeneous computing, where microprocessors are integrating CPUs, GPUs, and other specialized accelerators, all sometimes on the same chip. For example, you have AMD's APUs, Intel's Ponte Vecchio, NVIDIA's Grace Hopper. Just to talk about NVIDIA's Grace Hopper, it basically combines both a CPU and GPU on the same die. So you have a traditional ARM-based multi-core CPU, which is Grace, and you have a CUDA type accelerator called Hopper, all on the same microchip. What this poses to the programmer is an increasing complexity in programming and obviously a lot of memory bottlenecks, because both these accelerators and CPUs, etc., are accessing the same kind of memory. Then we have domain-specific processors. These are custom microprocessors optimized for very, very specific tasks. For example, there is the Google Tensor Processing Unit, Apple's Neural Engine, which goes into many of their devices like iPads, MacBooks, and iPhones, the Tesla Dojo, which goes into their cars. So This gives the opportunity for having extremely high efficiency, especially for very specialized tasks, typically which are based on artificial intelligence. For example, the Tesla Dojo, which goes into their vehicles, needs to do on-the-fly computations for automatic self-driving. And this is a very specific kind of calculation, and the domain-specific processor has been designed for that specific calculation. The challenge is that these specific processors are essentially very limited for general purpose calculations. So their applicability is very, very narrow. Obviously, there's a big role in the increase of GPUs in high performance computing. It is used largely in artificial intelligence and scientific computations. As the GPUs grow, the amount of cores that they have, or tensor cores, is increasing a lot. That means the amount of parallel execution capability that they have is increasing. The newer GPUs also have a high throughput and have higher memory bandwidths, which enable us to move data more efficiently from the host to the GPU and within the GPU as well. But the problem that comes with this is that obviously these GPUs, which were initially very lightweight and energy efficient, and are now becoming very high power consumption devices. In fact, the modern GPUs today consume more power than the CPU itself. To add to this challenge, there is more complex memory management, especially if you have multiple GPUs on the same workstation, where you have to look at things like unified memory. Finally, you have the RISC-V and other open source type microprocessors. RISC stands for Reduced Instruction Set Computing, and V is the version number 5. So these are open source instruction set architectures which allow people to do custom processor design. For example, a lot of the processors which are in the market, like the ones which run the Raspberry Pi, the ones which run Apple's M1, M2 processors, are all based on these sort of architectures. So this sort of gives some sort of democratization of processor innovation, which was formerly held by only few companies. The challenges to this kind of system, where you have sort of an open source instruction set architecture, is that whether the ecosystem of the compilers, of the other software tools which will run on this particular hardware, including operating systems, whether they are mature enough, because they have to be developed in conjunction with the development of this hardware. The other challenge is always memory technology, and this memory technology is very important for future microprocessors. We have noticed that while microprocessor technology on the compute side is increasing dramatically, memory technologies are not increasing at the same pace. There is a need for extremely high bandwidth and low latency memory, because we want to push large amounts of data very quickly and access this data very quickly while we want to do compute. So with regards to this, new types of memory such as HBM or high bandwidth memory, DDR5, persistent memory like Optane and MRAM are being designed. But the challenge again comes here is that if you have the memory which is of high bandwidth and low latency, the power consumption increases, and so does the cost of production of these sort of memories. So they are at now used only for high-end purposes. The other way of improving efficiency is moving beyond the monolithic chip design to look at stacked architectures which are in 3 dimensions. For example, AMD's 3D V-Cache is used for improved gaming and workload efficiency. Intel's Foveros 3D packaging is used for heterogeneous integration, and TSMC's CoWoS and Info technologies. So the opportunity here is that you will be able to get higher performance per watt of energy that you actually spend, and you have better customization of chip designs for very, very specific workloads. The challenge over here when you have 3D structures is the thermal management and heat dissipation, and also between the stacked layers to have very efficient interconnects so that the communication can take place efficiently. The next thing that we look at is cloud-based high-performance computing. So today there's a shift from owning the high-performance computing hardware at your premises to moving the workload to a cloud-based service. So the cloud-based service is essentially a remote service where physically the machine is at some other location. and you're able to sort of synchronize several of these machines which are kept across the globe. So once there is a shift to a cloud-based microprocessor, there is a reduced dependence on the on-premise supercomputer. The advantage of this is for a user, you can also use the pay-as-you-go model, which enhances the accessibility for small users. For example, there's no initial large capital investment. You can only have operational expenses which go towards the cloud computing charges. So the examples of cloud HPC solutions are AWS's Graviton, which is an ARM-based processor for cloud efficiency, Google Cloud's tensor processing units, which is very specialized for artificial intelligence training, Azure's HBV3, which is a high-performance computing cluster for scientific workloads. The challenges here on a cloud-based platform, because they do not run on bare metal, is the fact that how do you manage latency and bandwidth between distributed and compute nodes, sometimes which physically might not even be in the same place. And the fact that you're in some off-site remote location, you'll also have to worry about data security and compliance when there are multiple users from multiple different organizations or multi-tenant environments. When it comes to cloud computing, you have to look at cloud-native microprocessors. So why do you need custom processors for the cloud? First of all, traditional CPUs, which we have discussed, are not optimized for cloud workloads. Cloud workloads typically require very high energy efficiency and scalability. So if you look at the new cloud-based processors, such as Amazon's Graviton 3, which is ARM-based, which is optimized very, very specifically for cloud computing, and the Google Axion, which is for artificial intelligence-driven performance tuning for cloud services. This improves the energy efficiency and hence introduces cost-effective scaling for cloud service providers. And it has a far better energy efficiency compared to the traditional x86-based alternatives that we typically are used to on our desktops, workstations, and servers. So one of the things that we need to look at in energy efficiency in microprocessor design is to reduce the power consumption in modern chips. So we can reduce modern power consumption using techniques such as dynamic voltage and frequency scaling to adjust the power use, especially when the compute workload is not very high. So you can adjust the voltage and frequency to adjust it to the compute workload. You could also have advanced power gating techniques to deactivate unused sections of the chip. Let's say certain instructions are being run and not all the logical circuits in the CPU are being used. So you can switch off certain sections of the microprocessor. And then you can obviously use low power architectures like ARM for getting efficiency gains on cloud and mobile computing. There are also severe security challenges in microprocessors. The emerging threats look something like side channel attacks, because they could have multiple processes which are running on the same machine, and using side channel attacks, your compute could sort of get compromised. The other issue is in the actual manufacture of these microprocessors, because there could be supply chain vulnerabilities in microchip fabrication. That means I will not be getting these advanced chips for use immediately. But when I'm looking at security issues, there are many innovations which have come up, like security enclaves like Intel SGX and AMD SEV to protect sensitive computations from side channel attacks. You have hardware-assisted cryptographic acceleration. And one of the biggest challenges is that once quantum computing becomes realizable, it will have a big effect on cryptography. So post-quantum machines, we need to have specialized cryptography for future-proof security. One of the things that will help us in the future is artificial intelligence-assisted microprocessor design. So here we use AI to accelerate the chip design, and we use an AI-powered layout optimization for better power and area efficiency. Machine learning-driven workload prediction to optimize execution paths. So simple applications like Google's deep reinforcement learning for chip design, which speeds up the placement of transistors in silicon. And also NVIDIA's AI-powered compiler optimization, which does auto-tuning for code execution on GPUs. Finally, we would like to talk about the role of edge computing in future architectures. We need to move the processing closer to the data source. The reason why we need to move processing closer to the data source is the fact that we should have reduced latency for real-time applications. And Moving the processing closer to the data source will also result in lower network congestion and also cloud dependency. So you need to develop smart Internet of Things chips optimized for AI inference, for AI workloads at the edge or where the data is actually. For example, Tesla's full self-driving chips, which actually do the compute right on the vehicle and do not depend on any sort of remote compute, is a good example of how edge computing is being done. The challenge obviously is that how do I have energy efficiency in these small scale devices? For example, in a self-driving car, if I have a chip on board, how do I do efficient computation which does not take up too much energy and is able to work in a complicated environment? And also, this is a decentralized network, so how do you ensure security of data when you're processing this sort of computes? When it comes to the software side, this is a big challenge in software and programming. So adapting this software to these new hardware architectures where there is multi-threading complexities, especially in heterogeneous computing. Trying to manage the different memory hierarchies across CPUs, GPUs, accelerators, and these new domain-specific processors is going to be a big challenge. So we'll have to look at new programming frameworks like SYCL, One API for cross-architecture compatibility, and look at frameworks like Cocos and Raja for portable performance in scientific computing. So if you look at the future trends of the data center microprocessor, the next gen exascale computing, it usually will combine artificial intelligence acceleration with traditional HPC workloads. So we're going to look at custom SoCs or systems on chips for large-scale scientific simulations. An example of these sort of machines is Frontier at Oak Ridge National Labs, which is an AMD-based exascale machine, and Aurora at Oregon National Labs, which is an Intel Xeon-based supercomputer. The other technologies that are coming in to microprocessor is photonic and optical computing, where we use light instead of electrons for computations, and optical interconnects for high-speed data transfer. At the moment, there are lots of fabrication difficulties in these sort of microprocessors, and we also have a challenge with integrating them with silicon-based chips. But this is something which engineers will probably resolve in the future. Finally, the biggest challenge is a unified memory architecture for microprocessors. So today you have the CPU and GPU memory valve, where you have to explicitly transfer data from the host to the device and back and forth. So once this device wall is sort of broken, you'll have a unified memory for seamless data sharing, which is typically a large bottleneck. The challenge behind this is to have coherence for the memory, consistency in the models, and obviously scalability. Thank you.